Welcome to the solutions for the Cape Computer Science paper. If you hear me sniffling, it's because I'm battling a slight bug. If you find my eyes are red, it's because I'm congested. Huh? No, try not to sneeze. Try not to sneeze. Nope. No sneezing. No sneezing. I am not going to sneeze. Alright, let's get this out of the way. Woo! Yeah, I'm battling a little cold here earlier, so don't fight me too much if I sound very nasal and I sound very sound sick. Yeah. The reason I'm working it out without looking at it in advance is because I want to give you the actual real impressions on how I feel about particular questions. And you might actually see me make mistakes because it's more relatable to students when they see teachers make the mistakes and then work it out still, because that helps you think through things instead of thinking that we have everything under control. Nope, we make a lot of mistakes too. And there are times when we misinterpret a lot of questions. And I want to sneeze, so I am going to... Section 1. This is supposed to be the architecture and subsection. State the function of each of the following registers that are commonly found in a microprocessor. IR, instruction register, stores the current instruction being executed by the CPU. I guess so. Usually when they have a definition question, most children, we have a little problem with the definition question because there is no actual textbook way to look at that. So I guess it will store the current instruction as being executed by the CPU. Yeah, currently being run. Currently is the word. Current, yeah. MER, memory address register. The memory address register that stores the location of the next yeah, the MER stores the yeah, we have a problem here. The difference between the MER and the MDR, they're very, very close to each other. So you had to kind of write something that'll differentiate both of them. If I had to differentiate both of them, I had to think a little bit, because some computers don't have a MER, they have a MDR. Alright, they put the memory address that is currently being used in the fetch execute cycle. Yeah, put up. Yeah, as I said, MER and MDR kind of different, but let me go with that now. Yeah, and the MDR, memory data register, well, that's actually data that you got from the memory address, right? Yeah. So this is like a temporary location to store data that is fetched from memory. Yeah. So the MAR kind of points it and the MDR holds it, basically. We'll go with that. Alright, that's part one. Explain how hard this differs from RAM in terms of access method and access speed. Cake. And you see questions like this, you just kind of be like, yeah. So let's go with method. Yay! You just crushed it there. Explain how RAM differs from flash drive in terms of volatility and portability. Look at us. Volatility. VOLITALITY. RAM is volatile because when power is taken, it's what's the word, boy? It is lost. Not it is lost, data is lost. Data is lost. And portability, flash drive retains the data. Then we have portability. RAM cannot be transported. RAM data. Flash drive data can. Yeah, it's 3 marks. I mean, come on, it's 3 marks. We proceed now to see part 1. Describe the term instruction format. What do they mean by instruction format, boy? Now, they could mean 2 things here. It could mean the instruction format is more like the way that you organize the bits. 2 marks, they talk about opcode and operand. Yeah, opcode and operand, definitely that's what they're looking for. So let's go with the format is how the opcode and operand are split when using a particular set of bits. Example, 32 bits. Yeah, we'll take that. Yeah. 2 marks, that's probably what you're looking for here. Describe the following adjustments. Oh, they just say to describe it. This is using the opcode and one operand to carry out an instruction. You can also put a little example, put a little example because, the little example ain't gonna hurt nobody. Right? So example, move AX. Right? That's one address. 2 address, using the opcode and 2 operands to carry out an instruction. Example, move AX, comma, PX. Yeah. Taking that. Alright, so first question, cake, eat, leave no crumbs. This is how we handle the first question there.
It's got such a long, thin neck. Oh! No.
Take that food, boy, take that food. Alright, the following is the truth table for a certain circuit. Draw, design a circuit diagram represented by the truth table above using only primary logic gates. This is the sum of products. So this is a product here, this is a product here. This is one set of products, this is the next set of products. So we're gonna have a or sum of products. The top one is not A and not B, or A and B. Yeah, because this is the not A and this is the not B, and this is the normal A and normal. So whenever you get a 1, that's where you're trying to use the sum of products. So if we were to draw this, hit them with our OR gate there. Boom. What's the output? D. And then you have 2 inputs coming in. Where those 2 inputs going to end up? We don't know. You're going to get a AND gate. You have the A and the B. A and B. This one is going to have a not A and a not coming in. And this one here just going to have a normal AND. Ta-da! Yep. That looks like it there. Only primary logic gates. So you can use you could have taken these 2 here and make a NAND gate, but a NOR gate, sorry, a NAND gate, but they only say primary logic gates. So that's the primary only. What you want to do is you want to label the letters so that you'll make sure you get your marks, A and B. Label them. How much marks in that? 4 marks? Cake. Yeah. So the tricky part of this question is that it's an XNOR, but they say only using only primary logic gates. So you have to show the primary logic gates. If you don't show the primary logic gates, which are only and or not. So you have a and here. Yeah, sorry, a or there, and a not. Primary. Tough. Yeah. Part B. In a security system, 4 sensors are used to transmit data to a single line for alarm notification. You send explain a multiplexer. This is our carbon copy question from I think 2015 or 2016, by I don't know, but yeah, there's a carbon copy. Been here, done that. The multiplexer will have a clock signal. Wow. On the selection switches. Three marks, yeah. In this question. So a multiplexer is going to have the ability to, like, you have 4 inputs. Camera 1, 2, 3, 4. And then you have the selection switches. And when the selection switch is 0, the camera from here will get sent out. And when the selection switch is 0, 1, the camera from here will go through. When it's 1, 0, the camera from here will output. That's basically how a multiplexer works. Draw a coil. Oh, wow. Then they asked it to draw it. I just drew it. Way. I should have gone reading. Let's just take this whole thing here. As I said, let's just take this whole thing here and drag it right there. Boom. 4-to-1 multiplexer. out. So really the coolest thing about these past paper videos is that I get to explain while doing a question. So a lot of you would learn things that you never saw before just by me working on the question. But sometimes I can't explain every single thing, and I don't know, you might need help explaining. So 3088799, WhatsApp that, and find out what we have available. It might be a crash course, it might be a class. Remember, when you join my classes, all of the classes are recorded, so you'll get to see every single thing that we did from the start of the syllabus. So if you're not sure about certain questions and you're not sure because the explanations I give in the past papers are a little too fast, then WhatsApp the number, see what we can do for you. If not, hope you enjoy the videos and hope you learn a lot while you go through these past paper answers, right? Cool. Next up, it is part C. State the smallest and largest integers that can be stored in 8 bits when signed magnitude representation is used. 8 bits? What? When you sign on magnitude, you could start with 1. Oh, smallest integer will be negative right here. So 1 will be the negative number, and you have 1, 1, 1, 1, 1, 1, 1. What I convert into where? Guys, 64, 0, 1, 2, 4, 8, 16, 32, 64. That's 127. Negative 127. And then positive 1, 1, 1, 1, 1, 1, 1 will be positive 127. 128? 128, my bad. Yeah, 128 will be the answer, yeah. Ooh, I had a brain freeze there, yes? Okay, cool. Calculate the 8 bit 2's complement of negative 87. So we're starting off with 87, negative 87. We take out the sign. Why did I write 85? 87. So you get 87. 87 in binary is going to be, I really go and divide by 2, right? No, I'm a professional. Actually, I'm going to divide by 2. 2 into 87 is going to be 46 remainder 1. No, 43 remainder 1. Because maths. Yeah, 2 into 8 is 4, 2 into 7, 3 remainder 1, yeah. 2 into 43 is 21 remainder 1. 2 into 21 will be 10 remainder 1. 2 into 10 is 5 remainder 0. 2 into 5 is 2 remainder 1. 2 into 2 is 0. No, 2 into 2 is 1 remainder 0. 2 into 1 is 0 remainder 1. So technically I'm supposed to get, 1 0 1 0 1 1 1. That correct, boy? Let me see if I'm going crazy here. That is 1 plus 2 plus 4 4 8 16 16 32 6. So 64 and 16 is 6 7 80 84 5 6 7. Yeah, that's yeah. Alright, so that's 87. I don't know if they allow you to carry a calculator into the exam, but I think you should be able to. Our calculator do not very easy. Alright, so we convert it, and then we have to what? Invert it. Invert. Shucks, I'm supposed to be working out all on red here. Invert, which will be 0 1 0 1 0 0 0. And then plus 1, add 1, which will be 0 1 0 1 0 0 1. Ta-da! Do I have to change back the first bit? Oh no, it's 8 bits. I forget the 8 bit. Sorry. 1 2 1 2 3 4. Alright, so the 0 here will convert to 1, and alright, then you get the 1 there. Alright, my bad. I forgot that it's 8 bits. Don't ever forget that it's 8 bits that you're dealing with, so you have to fill up the extra bits when you do your calculation. Because I ended up with 7 bits, and I had to put the 8 bits. When you invert that, you'll get 1, right? Good, yeah, so. Right. 2's complement done. Alright, that's it for module 1. Module 1 was cake.
Sometimes my genius is, it's almost frightening.